Dear students, if you remember correctly that in the last class in the classroom we talked about the Green's function in a plane, in a complex plane. We already proved Green's function, and also we proved Cauchy's theorem. Cauchy's theorem says that if a function, say f of z, is analytic in a region, say R, suppose this is the region R and this is the boundary C, then if this function is analytic in this region and also on the boundary, then Cauchy's theorem says integration over the path C f of z dz, that is equals to 0. Actually this is Cauchy's theorem and this is consequence of the Green's theorem. Using Green's theorem and the condition for analyticity of a function, which is basically Cauchy-Riemann's condition. So if you couple together, then you achieve this condition, which is called Cauchy's theorem. Now from this we can have yet another consequence which is very important. It tells us that if a function is analytic in a region, then the integration of the function in that region from one point to another would be path independent. That means, suppose you have a region R, this is the region, and this is a z plane, say, and in this region the function, say f of z, you defined as f of z, this function is analytic in this region. Then if you integrate from one point A to point B, if you integrate f of z dz from A to B, that integration carried out this way, if you move along this path, then the integration value you get would be same as if you carry out the integration from A to B along this path. That means in whichever way you go from A to B to carry out this integration, the value would be the same. It is similar to a conservative force field. Okay, so it is path independent, and it will be very useful, in complex plane. If you want to carry out a very complex integration of an analytic function, then you can choose the most convenient path to evaluate the integral, because it is path independent. So this is very interesting and very important. We can prove this. Let's say again from A to B, I just take a closed contour. This is a C. From point A, this is say D, then B, and this is say point E, and then come back to A. Then according to Cauchy's theorem, over this contour the function is analytic, and therefore f of z dz, that should be equals to 0. Now this contour I can just take the partial path and then add them to make this contour. And first I go from A to C to B, f of z dz, plus then I complete from B, E and A, f of z dz, that should be equals to 0. That means integration A to B through C, f of z dz, A to B through D, that should be, now this is B, E, A. I can reverse the path with a negative sign, so minus A, E, B, A, E, B, A to B through E, okay, f of z dz equals to 0, right? A to B through D minus A to B through E, that should be equals to 0. That means integration A to B through D f of z dz equals to integration a to b through E f of z dz. Okay. This is the integration when I am carrying out from a to b through this path, along this path, is same as the same integration from a to b along the another path, and therefore it proves that the integration of analytic function from one point to another is path independent. Okay. Now what I will do, I will take a multiply connected region and I would see the consequence of this Cauchy's theorem. What is multiply connected region? A region, okay, a region, say this is R, and this is bounded by say C1, and another boundary is say C2. Now this is the boundary. If you can shrink it to a point, then it is called a simply connected region. If you cannot shrink it to a point, then it is called a multiply connected region. You see, if you try to shrink this circle, you just get stuck here. You cannot go beyond that because the function is not analytic here. So this is a multiply connected region, and this region, this analytic region, is this region, and this region is bounded by C1 and C2. Therefore, a function f of z which is analytic in this region, if you perform an integration over the closed loop dz, that should be equals to 0. Now what is the closed loop? Now suppose I start from here. This is the point A, this is the point say B, and then you come here, this is the point D, then travel this way, you travel this way, then travel this way, D, suppose this is E, this is say F, and then again come back to D and travel this way. Earlier you came this way, now you are coming this way, then again go to B, and then say F, now suppose this is G, and come back to A. So A, B, D, then E, F, D, then go to B, and then G, A. Okay, so then I can write this as I go along from A to B to D to E, F, again D, then B, then G, then A. Okay, f of z dz equals to 0. Okay, f of z dz equals to 0. Now if I break these paths, then it would be integration from A to B f of z dz plus then B to D f of z dz plus integration D E F D f of z dz plus integration D to B f of z dz plus D to B, then again integration from B G A f of z dz, that is to 0. Now you see that this path is from B to D and this is D to B, means B to D and D to B, they are in opposite direction and therefore they will cancel each other. Okay, so you are left with integration. Now see A B and this is BGA, A B BGA. That means if you couple these two, they give me C1, the path C1, f of z dz, right? Then plus DEFD, okay, as it is DEFD f of z dz, that's equals to 0, and therefore integration C1 over the circle f of z dz, this will be a circle, this is also a circle. Now I travel this way, right, and then I can reverse it with a negative sign here, then make it like closed circle, C2. C2 is traveling this way. Okay, C2, the contour. Then f of z dz equals to 0. And now if you remove this equals to this, and therefore it tells me that if we consider a multiply connected region, then the integration of a function which is analytic in this region, that integration over C1 is equals to the integration of the same function over this circle C2. Okay. Now, based on these things, I am just trying to evaluate an integration. Okay, so let us look at the application of this theorem. Say I am asking you to evaluate integration over the closed contour C, where C is a simple closed curve. Okay, simple closed curve. Now I am asking you to evaluate this integral for 1 when z equals to a is outside the circle, and number 2, z equals to a is inside C. Okay, so these are the two questions I am going to ask you. Now first one is simple, because you see, suppose this is C, okay, and your function here is 1 by z minus a, and this point is a, z equals to a is outside this circle. Okay, if it is so, then this function is not diverging inside this circle, and therefore it would be analytic in this region according to Cauchy's theorem. Integration f of z dz equals to 0. That means integration dz by z minus a equals to over this would be 0. Yeah, simple as that according to Cauchy's theorem, because this function is analytic in this region. Okay, and this function is diverging point is outside the circle. But now if this diverging point is inside this, that I can do it here, because we can use these formulas. Now suppose the same region, but here is z equals to a, so this is your circle C. Now what I do, I consider a circle, say I give the name tau, with a radius say epsilon. Okay, epsilon. Then I should say z minus a equals to epsilon e to the power I theta, right? Then z equals to a plus epsilon, where epsilon is pretty small, I theta. Then dz equals to I epsilon e to the power I theta, right? Then integration over tau, over C actually, over C, dz by z minus a, that should be equals to integration over tau dz according to this theorem, dz by z minus a equals to integration, what is dz, is this I epsilon e to the power I theta and also d theta, right? So d theta divided by z minus a. Z minus a is how much? Epsilon e to the power I theta. This cancels, this cancels, this cancels, this cancels. Now this is over tau, right? So tau is some, it makes a circle, complete circle from 0 to twice pi. Theta is the variable, and therefore it is twice I pi. So the value of this integral when z is inside the circle, then its value is twice pi I, but this value is outside this is. Okay, so this is one example using this Cauchy's theorem that we have I have worked out, and I hope you understood. So let me stop here with this lecture, and again we will meet in the next lecture. Thank you.